This video is on bond polarity and electronegativity and comes from section 8.3 of your textbook. So let's think a little bit about covalent bonding. So if we have a chlorine molecule, so that would have the formula Cl2, then our Lewis dot picture says that we've got two chlorine atoms. And a chlorine atom has 7 valence electrons, so I'll draw those 7 valence electrons in there. So this is our Lewis dot symbol for chlorine. So if we have another chlorine atom, we've got the same situation going on, and we know that they're going to agree to share this one lone electron that they have. And so that produces a bonding pair of electrons, and we call that a covalent bond. So these two atoms are agreeing to share this pair of electrons. So this is sort of the Lewis dot picture that we have going on. Now, in reality, what's going on, remember we've got an atom, and an atom has a nucleus, and in the nucleus of an atom there's some sort of positive charge. So I'll draw a plus sign here, put a circle around that. And we also know that there's this valence shell. So I'm going to draw this outer circle. That's our valence shell. And so in that valence shell there are going to be some electrons. So I'm going to put some other dots here. These are the electrons that we're imagining that are being shared between two atoms. So let's imagine that I have another atom that's trying to share these two electrons. So that's an electron there. So here's our other atom, and it's also going to have a positively charged core right here. So there's the nucleus of the atom with the positive charge. And it has some sort of valence shell too. So I'm going to draw the valence shell in here, and I'm going to have them kind of intersecting like this, indicating that those two electrons are being shared between these two atoms. So I realize it looks kind of wonky, but you get the idea. So these two electrons are then being shared between these two atoms. Now, what causes these electrons to be held at these two atoms has to do with the force that they feel. And that's going to depend on the charge of the nuclear core. So the bigger the charge, the greater the force, and also how far away these electrons are from that nucleus. So that sort of gives an average force that an electron will feel in the valence shell of the atom. So let's imagine that this atom over here has a really big positive charge. So I'm going to make this plus sign really big so that we understand that this is a big positive charge that's over here. And because that charge is big, and maybe this electron happens to be close to that big positive charge, this electron that's in this valence shell is going to be held more closely to this atom over here than the electron over here to this atom. So this would not be the case for chlorine, because in chlorine the nuclear charges would be exactly the same, right? So if you had some different situation where maybe you have an F atom and a hydrogen atom, well, in that case the electrons are really close to this fluorine atom. The fluorine atom has 9 protons in the nucleus, so maybe these electrons are going to be held really tightly by that fluorine atom. So what that's going to mean is that this shared pair of electrons, well, they're going to spend more time kind of buzzing around this fluorine atom than they do around the hydrogen atom. So most of the time they're buzzing around this fluorine atom, and occasionally they come over here to this hydrogen atom. Most of the time they're over here. So we call that unequal electron sharing because most of the time the electrons are being pulled over here. So this is kind of like the kindergarten student that likes to hoard all of the toys and not share very well with the other kindergartners. So fluorine is like that. It pulls the electrons towards itself, creating a higher distribution of electrons. So that we would say that the electron density over here, so let me write that because that's kind of an important term in chemistry that we talk about a lot, is electron density. So density we know is something per unit volume, and so this is the number of electrons per unit volume. And so since these shared electrons spend more time over here, the average electron density is going to be a little bit higher over here. So it's like a thicker cloud of electrons over here than for the hydrogen atom. And that creates what we call a partial negative charge over here. So I draw that using this symbol. So this symbol that I just drew, it looks kind of like an S but closed off here. So maybe it's kind of like a golf club with a bent shaft. So that's the lowercase Greek letter delta. So you remember from some of our other work in chemistry that delta means difference. So we talk about delta E or delta H. That means differences in enthalpies or differences in energies. So delta is for a big change. So we're going to use the lowercase Greek letter delta if we got a small change. So because these electrons are over here a little bit of the time, more often than over here, that makes this side of the molecule a little bit, small difference, negative, and so we put a superscript minus over here. Whereas this poor hydrogen over here, because it doesn't get those electrons as often, what you see is more of its positive core because the electron density has been stripped away and shifted over this direction. So this side of the molecule is going to pick up a partial positive charge. So that creates a molecule with two different ends, a negative end and a positive, an electrically positive end. So we call that an electric dipole. So dipole is just a word that means we have two ends, and in this case we're talking about electric charges. So this is something that has two ends. Poles have two ends, right? Dipole, we've got two ends, di means two. And so we've got an electric dipole, two different electric charges here. All right, so now we see how we can have unequal electron sharing. So I told you that fluorine pulls its electrons more closely than hydrogen. You might be wondering, well, how did I know that? Well, I know that because we can actually look at a whole bunch of molecules and kind of measure this property. And so we define something called electronegativity, and so that's our next topic. So what this is it's a scale that we've invented. We can connect it to things that we can go out and measure, and they're going to tell us how strongly an atom is going to hold on to electrons that happen to be in its valence shell. So we're going to assign an index, a number to that. And so we're going to measure these things according to this scale. So the scale is a little bit arbitrary. We kind of have to agree on a convention. So what kind of measurable properties are you going to relate it to? And then you go out and do that. So this is related to measurements, but electronegativity is not something that you can actually go out and measure directly. So there's no electronegativity meter. It's based on this arbitrary scale. So what does it do? It measures sort of the pulling power, the holding power of atoms to electrons. So it tells you how strongly an atom will attract electrons in its valence shell or when it's bonded. So higher electronegativity means more attraction. So here's the graph of this scale, and this scale is due to Linus Pauling. So this is his convention, and this is one that's sort of the most popular, at least it shows up the most in general chemistry textbooks. So you can see that generally this follows the same trend as ionization energies that we've seen before. So we have high electronegativity out here in the fluorine corner, so this is high electronegativity, and low electronegativity down here in the cesium francium corner. So down here this is low electronegativity. So as you go from corner to corner then, electronegativity is going to increase. And the one that you're going to kind of have to remember right here is our oddball hydrogen. So hydrogen has an electronegativity that occurs right about here, in between boron and carbon on this scale. So a couple of things to point out. You see that the nonmetals up here generally have high electronegativities. Semimetals are kind of in between. And the metals have low electronegativity. So again, there's that periodic table pattern. So we would expect these guys to pull strongly on electrons in bonds, whereas these guys will not pull strongly on electrons in their valence shell. So now we can begin to think about unequal sharing in a molecule, and this produces something that we call bond polarity. So let's think again about chlorine, dichlorine, Cl2. So in this case we've got two chlorine atoms. They're absolutely identical, and so they're going to pull equally on their shared electrons. Now what's being pictured here is something called a contour map, and we've seen those when we looked at quantum mechanics before. But this is just kind of a picture, a surface that tells us, hey, 99% of the chance the electrons in this molecule are going to be inside that shape. And so this might be a pretty good representation of what this molecule might actually look like if you could see one or hold it in your hands. Of course, don't know if it's yellow. That would be a silly question. You can't really have color at that scale. Anyway, so what we've got here then is this other color that's telling us something about the charge on that surface. So the more red it is, the more negative the charge, and the more positive it is, the more blue it is, the more positive the charge. So this might represent a full -1 charge. So if you see a really deep red color, that's a full -1 charge on some atom. So that would be like an ion. Similarly, if it's this deep blue color, that would be a full +1 charge. But we might have charges that are partial charges in between. So here's that little delta, delta plus and delta minus, for partial charges that are in between 0 and -1 or 0 and +1. So you see that chlorine right here is 0. So there's no net charge anywhere on the surface of this molecule. So we call that molecule we call the bond between these two atoms. So there's a chlorine nucleus here and another one over here, and this would be that bond that we're representing. So we call that bond a pure covalent bond. It's also sometimes called a nonpolar covalent bond. And that's when you have a perfectly even charge distribution. Now if we look at a molecule like HCl, and we go back to our electronegativity table, then we see that chlorine has a higher electronegativity than hydrogen. That means that chlorine is going to pull that electron density away from the hydrogen. So here would be our chlorine atom on this side. Here's our hydrogen atom over here. Electron density moves this way. We end up with a partial negative charge on this side and a partial positive charge on this side. So that creates a bond dipole, and we would call this a polar covalent bond. So this word polar means it's related to dipoles. That means that this molecule has two ends, and this bond has two ends. There's a negative end and a positive end. So this would be a polar covalent bond. And that's when we have that unequal sharing of electrons. Now you might imagine that we have two atoms that have a really big difference in electronegativity, like sodium chloride. So sodium chloride, again, chlorine has an electronegativity of 3, and sodium has an electronegativity of 0.9. So there's a big difference in electronegativities there, and what happens is the electron spends essentially 100% of its time buzzing around the chlorine, 95% of its time, and very rarely is there enough pull on that sodium atom for that electron to spend much time around that sodium atom. So we end up with this atom over here, at least one end of it, essentially being a full -1 charge, and this end being essentially, but not quite, a +1 charge. And so we call that then an ionic bond. Okay? So the bigger the electronegativity difference, the more our compound looks like an ionic compound. So if the electronegativity difference is 0, it's pure covalent. If it's somewhere around if it's somewhere in between, if it's kind of moderate, we say it's a polar covalent bond. And if it's a really big difference in electronegativity, we call it an ionic bond. So what's the dividing line for these? Well, this is kind of arbitrary, but your book and a lot of books will kind of use this one. So if the delta electronegativity, so I'm going to write it this way, so if the difference in the electronegativity between two atoms is less than about 0.4, we're going to call those pure covalent or nonpolar covalent. And so if the electronegativity difference then is in between, say about 2 and 0.4, and again, this is kind of fuzzy, a little bit arbitrary, these dividing lines, then we're going to call it a polar covalent bond. And if the electronegativity difference is then greater than 2, we're going to call it an ionic bond. Okay, so as we change that electronegativity difference, we change over from being a purely perfect sharing situation to a very unequal sharing situation where we've essentially taken the electron and given it completely to the other atom. So we can talk about how polar a bond is. So I describe this as the degree of polarity. And we can measure that by looking at the difference in electronegativity. So it's just two numbers, so you just calculate their difference. The bigger that difference, the more polar the bond is. And the larger the partial charges will be on those atoms. So here we have HF, which has a delta electronegativity of 1.9. And so the covalent bond between HF is going to be the most polar covalent bond. And so this is the most polar covalent, and it will have the biggest partial positive and partial negative charges on either side of that bond. Whereas HI has an electronegativity difference of 0.4. So that is almost a non-polar covalent bond. And so this one is just going to have a really tiny, so I'll draw a really small one right there, really tiny partial positive charge there, and a really tiny partial negative charge on the other side. So the bigger that electronegativity difference is, the more polar the bond. So finally, and we've already hinted about this, most things in nature are not purely ionic, purely covalent, or purely metallic bonding. Those classes really represent extremes. Most bonding is kind of in between, right? That polar covalent kind of thing. So we've already seen by looking at differences in electronegativity, so I'm going to draw a little line here. We're going to call this delta En, that when the difference in electronegativity is high, then you tend to have things that look ionic. So ionic is going to be up here on our little graph that I'm making. And if the difference in electronegativity is low, then those things tend to be more pure covalent. So that's a little bit about the difference between ionic and covalent. So as you make that difference bigger, you become more and more ionic. So most things are sort of in between here, right? Well, what about this metallic bonding? Well, to talk about metallic bonding, we need to draw another axis here. So that's supposed to be a straight line. And what we're going to plot on this line is not the difference in electronegativity between the two bonded atoms, but the average electronegativity. So I'm going to put that in brackets and I'll write a subscript AVG to remind us that we're talking about the average electronegativity between two atoms. So when that average electronegativity is low, we've got two atoms with both really small electronegativities. So what are those going to be? Well, if we go back to our graph, we see things that have small electronegativities, elements with small electronegativities, are metals. So we've got metals that are bonding together. So we can draw sort of a picture that looks like this. I'm going to make a triangle here. Burp, burp, burp. Very good. So there's a triangle. So over here in this corner of the triangle, that's where we've got things with sort of a zero difference in electronegativity and a really low average electronegativity. So these would be things that are metals, because that's how you get a low average electronegativity, and they might be the same metal, in which case they have zero delta E. And so this would be sort of purely metallic bonding. So the most metallic compounds will be over here. So you might think of cesium over here. So a whole bunch of cesium atoms bonded together. They're going to bond in a metallic way. Now over here we've got a delta E that's equal to 0, but the average electronegativity would be high. So how would you get a high average electronegativity? Well, you need to bond two things together that have high electronegativities. So two nonmetals. What are two nonmetals? Well, they're going to be covalent compounds. So for example, over here where your delta electronegativity is 0, you've got something with high electronegativity. Well, that might be fluorine. So F2. So over here this would be the covalent side of our triangle. And then up here where you've got sort of biggish differences in electronegativity, but sort of in between average electronegativities, because you've got something with a small electronegativity like a metal bonded to something with a high electronegativity like a nonmetal, then we're going to have something that looks more like a purely ionic compound. So maybe cesium fluoride right there. So you've got a big difference in electronegativities between those guys. So way up here, the average electronegativity, you've got 4 with something really small, so that averages out to give you something in the middle. So this side up here is then going to be our ionic side of bonding. And so if you're sort of in the middle of this triangle, then where are you? Well, you're going to be somewhere in between covalent. That's supposed to be L-E-N-T, not covalent. Covalent bonding, excuse me. I was talking about that for this axis. This is metallic over here. So you're going to be somewhere in between metallic, covalent, and ionic if you're somewhere in between. So we can draw sort of, I don't know, rough fuzzy lines. I'm going to draw some fuzzy lines kind of dividing this area up, right? And so things that are over here, these are going to be what we call covalent compounds, right? Things that are up here, these are ionic. These are metallic compounds. What about these compounds in here in between this section? Well, you're sort of in between metals and covalents. And so these are what we call semi-metallic compounds. And these make up the very important semiconductor industry. So there are a lot of components down here that are ceramics and semiconductors that are in between metals and covalent compounds. And so if you're kind of close to one of these lines, we would expect you to have properties in between typical ionic compounds and typical covalent compounds. So in nature, there are a lot of things that exhibit this sort of in-between bonding. And these terms, ionic, covalent, and metallic, really represent extremes in the world of bonding.